Welcome to the second video of the year because we goofed up the first one. This is Algebra. We're doing notes number 1, real numbers and operations. For those of you following along at home, we'll be talking about these sets of numbers here. We have a little errata that we have to take care of here. I made a mistake in one of the pages, so pay attention. And here we go. So as you see, we've got these boxes that are beautifully color-coded. Oh, so nice, so nice. Except the red kind of looks like the orange, my bad. So here's how we're going to read this chart, okay? The real numbers are all the numbers that we know about, okay? They're real to you. There are such things as not real numbers, imaginary or complex. We're not going to get those this year. That's Algebra 2, okay? And they are truly the most beautiful numbers, in my opinion. But we're going to talk about the real numbers, the ones you're probably familiar with. So we'll start with the most basic. So if you go all the way down the chart, we have the natural numbers. It is the smallest set of numbers, okay? So think like Russian dolls here, right? We have this giant Russian doll, and inside we have smaller and smaller and smaller. If that doesn't work for you, remember the protractors? Oh, you guys aren't geometry, okay? Mama bear, papa bear, baby bear. They all fit inside each other. That's how bears work, right? Okay? Okay, so here we are. Natural numbers. 1, 2, 3, 4, 5, etc. How many natural numbers are there if we follow that pattern? Infinitely many. Yet it's the smallest set. How does, right? It's the smallest, right? It's the smallest of the Russian dolls.
Wait a minute.
That's the natural numbers. It's called the natural number because it's all natural. It's what you count your sheep with, right? Or your cows or whatever have you in Podunk, Illinois. Okay? Respect. So, you wouldn't count like your possums because you don't have any possums, okay? So you don't need the number 0. 0 is a relatively new number. It was invented by the Chinese, okay? And it's super useful from place value. And we'll talk about that in a little bit. You kind of know about it, I'm sure. The Romans, for instance, didn't have it. Okay? The whole numbers are the same symbol, thick N. And again, how you do it is you draw a regular N and then you go back and hit it twice, okay? So, and we have 1, 2, you can see this, correct? Okay. 3, and so on, okay? Good one, good one. This is the whole numbers. So we have N, again, like this, and we go back and hit it twice. Sub 0, that's the whole numbers, right? If we flip it, what we end up creating are negative numbers, numbers that are the same as the other ones, except they just go in the opposite direction. That minus sign implies direction, okay? Numbers have direction, okay? And all together, we call this the set of integers. So if we rotate it, we get this. N becomes Z. Let me say that one more time. N, if we rotate it, becomes Z. Those mathematicians, right? Like, you're like, idiot. Integer starts with I, but they're pretty clever, right? So far, here are the sets we know about. We know this set, right? That's the natural numbers, N sub 1. Then we know N sub 0, the whole numbers, which is just natural plus 0, right? And then we have the integers, okay? None of this includes fractions, by the way, right? The space in between numbers. Okay? All of these sets are infinitely big. If you start at 1 and keep counting, you'll keep counting forever. If you start at 0 and keep counting, you'll keep counting forever. If you start at 0, how can you count the integers? Which way do we go, right? Well, someone was very clever, okay? There's different kinds of infinity, countable and incountable. This is a countable infinity. You can count it. Not all the way, you run out of time, but you can count it. Here's the clever way of doing it. You start at 0, and you go 0, 1. And then you do its opposite, negative 1. Then you go forward, 2. Do its opposite, negative 2. 3, negative 3. 4, negative 4. 5, negative 5. 6, negative 6. Do you see how you can count that now? You can do it both directions at once. Super, super clever. So it's a countable infinity, but it's the biggest infinity we've encountered so far. Okay? Cool. So that was the integers, okay? Let me, do I have a black pen in here? I do not. Fair enough. All right, now let's talk about the rational numbers. The rational numbers, okay? The rational numbers are Q, set Q. That's an awful looking Q. Oh, thank you very much, but I needed a pen, not a marker. It's all good. Because I wanted to do this. So you can see it a little bit better.
Oh my goodness.
I know, right?
Oh my goodness.
I know, isn't it great? Like, yellow's a great color if you go over it in pen afterwards, right? So, rational numbers. starts with Q. And now you're like, okay, I get it. N for natural. Whole numbers are basically just natural, so they kept the same letter. Integer Z, we turn it. I get it. Q, bruh, right? Well, here's the deal. I'll walk you through my logic. Q stands for quotient. Q stands for quotient. What do quotients remind you of? Division. Wow, you guys remembered that word. Division. And division, all division is fractions, okay? So if I say 3 divided by 4, you know that 3 divided by 4 is 3/4, 3 over 4. Fractions are just division for lazy people, right? What's 7 divided by 12? 7/12. That's it. That's all fractions are. It's just division. And you don't touch it. This, go run a calculator, right? Figure it out. No, why? This is the right answer. You're done. Why did they make you do that in elementary school? I don't know. Because 7/12 doesn't come out evenly. You have to round it somewhere. So my answer is more right than yours. Your answer is an estimate. Mine is exact. It's 7/12, 7/12. I don't understand why they didn't teach you that, but we're going to teach you this year, and fractions aren't going to be scary anymore. So division is just fractions. Now fractions, like a third, is a comparison between two numbers, 1 out of 3, right? Like your batting average if you're doing all right. So fractions are just comparisons. And comparisons are just ratios. You've probably heard of this, right? 1 to 3. 1 to 3. It's about ratio of parts. So quotients just mean ratios. And if a number is a ratio number, it is a rational number. Boom. So quotients are just division. Division is fractions. Fractions are just comparison. Comparison is just ratios. So we're talking about the rational numbers, the rational numbers. Yes?
I said that you write your twos differently, but
I did do my twos differently. Oh, that was before I changed my twos. That was the year I taught that class. That changed everything. And this was the first algebra class I taught. Yep. My twos are goofy on this probably. Yep, right there. Yep. Okay, so the rational numbers are just the fraction numbers, the rational numbers, okay? Numbers you can write as a ratio. That includes decimals, okay? 0.35. Who knows what that is as a fraction? 35 over 100, right?
yeah.
Right? At first it seemed like, how would you do that? And then it was like, oh, that's not hard, right? Okay, all fractions are. But this also includes all the numbers below, because you can write 1 as a fraction, 1 over 1, right? You can write -1 as a fraction, -1 over 1. So rational numbers just fill in the space. So if we go back to our number line, rational numbers, the Q set, okay? There's my crazy Q. It fills in all the space, or at least most of it. Okay? I used that same color twice. My bad, guys. All right, so rational numbers fill in the space, but not all of it. I said most, and I said most, and that was incorrect. Actually, most of the space, almost every number, is in any of those. So go back to the chart. All of these are connected, right? Rational numbers and natural numbers are one and the same. Rational numbers just include more of them, right? And they're all connected. But here's the other side of the family tree. Irrational, the opposite of rational. And it turns out, if you add up all these numbers, there will still be infinitely many more irrational numbers. Think about it this way. Imagine a dartboard, and it has every number on it in existence, the rationals and the irrationals, okay? If you throw a dart, it is infinitely improbable, so not likely to happen at all, for you to hit any of these. That's how many of these there are. You'd think, oh, most common numbers are like 1, 2, 3, or maybe the fractions, right? No, it's the other numbers, the weird ones. So what are the weird ones, the irrational numbers? Well, rational means you can write as a ratio. It's a comparison between two numbers. Numbers like √2 and pi, you cannot write as a fraction. I know what you're thinking. Pi over 1. Right? No, it doesn't count, okay? Pi cannot be written as a fraction. It's not really the rule for irrationals. Really what we mean is that they go on forever and they do not repeat, okay? So pi goes on forever and has no pattern to it. You can't memorize it. Eventually, there will be a digit that you didn't memorize. Same thing with √2. It goes on forever and it does not repeat. Going on forever is not enough, okay? Because lots of numbers go on forever. For instance, is 1/3 rational? Can it be written as a fraction? Yeah, right? It's a comparison of two numbers. As a decimal, it does this, right? It goes on forever. That's a problem. That should be irrational. We have a contradiction here. No, because there's a pattern. 3 forever. You can memorize that. So that is a rational number. Whereas pi, even though you can write it as a fraction, it's irrational. It goes on forever and has no pattern to it whatsoever. Same thing with all these. So we have one family tree, which is the rational part of the real numbers, and the irrational part's over here. And there are more irrationals than rationals, even though there are more categories over here. The smallest set is the natural numbers because it's the most selective, right? It's only whole numbers starting with 1. Whole numbers is next most selective, right? We'll let 0 in. Integers say, we'll let the negatives in too. Why not? Rational says, we'll let in all the spaces in between. And then irrational says, not all the spaces. Some of the spaces. We have most of the spaces in between. And all together, they fill up the entire number line. And that makes the real numbers. Thick R. And that's the story of numbers. So as an example, each number according to the subset of the real numbers. So -2, what subset does it belong to? Give me one of the subsets. These are the sets. Which one does it belong to? Yeah, go ahead.
Integers.
It belongs to the integers, obviously. Does it belong to the whole numbers? No. What else does it belong to? Yes.
Natural numbers.
Natural. Is -2 natural? You wouldn't count your sheep with that. You're going the wrong way. It's not the natural. If it's the integers, it's going to be also in the what? I know it.
What?
The what?
The real number.
The real numbers. It's all numbers that we know in here are real. That's very good. So on your exam, when it says, hey, what set is negative, make sure you don't forget real numbers. That's like free points, right? Everything's a real number in here right now. Okay. So it's in integers, it's in real. Well, if it's in both of these, it must be as well, right?
Yeah.
They're connected. So we read it this way, not down, okay? So if it's in integers, it's going to be in rational, it's going to be real. All right, what about the number 5? What sets is it in? Yes?
National.
Natural, yep. What else?
Whole numbers.
Whole numbers, right? Because it's the same thing, just added on 0. And?
Integers.
And integers, and?
Rational.
And?
Real.
Very good. Is it irrational? No, 5 doesn't go on for it's easy to memorize. Right? This many. Okay? It's not an irrational number. Very good. Nice job. Let's look at page 2 now. It goes back through these and kind of defines them a little bit better. I have one thing to change. Can you tell me what's going to change? What about one of these definitions? What needs to change? Where's the error? There's technically 2. There's one big one. And it's not something that I wrote that's necessarily wrong. It's just something might need to be added to it. Yeah.
The irrational.
The irrationals, what about them?
It fills the gaps.
It does fill up the gaps. That's true. I'm going to tell you that the irrationals definition is wrong. Numbers that do not terminate. That's not enough. There are plenty of numbers that don't terminate, like stop, right? Like 0.3 repeating, but that's not irrational. What else do we need to know about it?
Numbers that do not terminate and that do not have a pattern.
And have no pattern. Good. Good teamwork, guys. And have no pattern. Can't be memorized, right? There's one other error. This one's a little bit harder. Rational number says integers, but also any number be expressed as a fraction. Well, pi can be written as a fraction technically, pi over 1, right? So really what we mean is and has a. Another way to say that is it terminates, meaning it stops, right? Like the Terminator. Or it repeats. Okay? Like 0.121, 0.1 or 0.121, 21, 21, 21, 21, 21. That repeats. It has a pattern, right? We can draw a little bar over it. I know, sick, dropping bars, right? Okay? Or it terminates. It stops, like 5.19. That's rational because it stops. Okay? You guys ready for the next page? Cool. All right, let's talk about the number line. The number line is continuous. Continues in both directions. Infinite length, okay? Forever. Less and less to the left and greater to the right. We decided to put 0 smack dab in the middle of it, and that's kind of our center point, right? So we have all the negatives and all the positives. We have their opposites on either side of 0. All real numbers can be graphed on a number line, so we can put them on here. So every number that we know, right, because we know all numbers, including irrationals, they fit somewhere on this line. We've talked about that, right? Here's our line earlier, and you can see where the numbers are, even though I doubled up these colors. Here's an example, right? And again, it goes from less to greater, shouldn't be complex. Root 2 is between 0 and 3, okay? Sometimes it's easier to see where a number lies if you change it into a decimal. I don't like using decimals a lot because they're harder to deal with than fractions. Trust me, I know you guys are the complete opposite right now, but by the end of the year, I think you'll agree with me, okay? But it is helpful to figure out where they sit. I can figure out that root 2 is somewhere between 1 and 3, though, because root means what two numbers multiply to make 2. Well, 1 and 1 is too small, and 2 and 2 is too big, right? So it has to be somewhere between 1 and 3, like 1 point something, right? Just a little bit more. Because if it was 2, it'd be too big, and 1 is too small. So it has to be somewhere between there. 1.4. Turn the page. Let's talk about powers of equality, properties of real numbers, okay? All real numbers have these properties, okay? Not all numbers do, but all the numbers that we know right now have these properties. First, the additive identity, okay? Additive, like we're adding something in, right? Addition. Identity means I am who I am, okay? So the additive identity says sum of a number and 0 is the original number. Now, I'm using letters. Some number. It's a variable, right? It could be any number. Plug whatever you want in. If you plug in 5 for A, you have to plug in 5 for A everywhere, though, okay? So 5 plus 0 is 5. Checks out. 6 plus 0 is 6. Negative 5 plus 0 is negative 5. It's the additive identity. If you add 0 to any real number, okay, real numbers, then it pops out itself. I am who I am. That's identity. Multiplicative identity. Multiplicative is in multiplication. Again, identity, I am who I am. The product of a number and 1 is the original number. Now, when we add 0, we get the same number, right? That's I am who I am. When we multiply by 0, do we get the same number?
No.
No. Common mistake people make. They think, oh yeah, it's the 0 ones, right? No. I am who I am. I start and end the same. So this one, it's multiplying by 1. That's the multiplicative identity. Easy for me to say. So here's some examples. 7 plus 0 is 7. Root 2 times 1 is still root 2. Okay? You need to know the names of these things. We are going to talk about them a little bit, okay? I know they're silly, but they're important. Turn the page. Additive inverse. So additive means addition, right? So when I ask you to identify these, you won't circle something with multiplication in it, right? You'd be surprised. Inverse means to undo. Okay? Like Bizarro Superman. They meet together with regular Superman and they collide and annihilate like antimatter and matter. So additive inverse, the sum of a number and its opposite is 0. So here's A. Opposite of A is negative A. Does that make sense?
Yes.
Right? Plug in a number like 5. 5 plus negative 5. Oh, checks out. That's 0. I put a slash through my 0 sometimes, that way you don't think they're O's. Okay? So additive inverse means if you add a number and its opposite, it always goes back to 0. Multiplicative inverse. Again, inverse means to annihilate or cancel out, right? Multiplicative means multiply. So it's going to be something with multiplication, and we're going to end up with something annihilating. Now you might think, A times 0 is 0. Ah, that's annihilation. Okay? This is a confusing one. The product of a number except 0 and its reciprocal is 1. Reciprocal. Word of the day. Okay? Here's how reciprocal works. Okay? If you're in a relationship, you love somebody, but they don't love you back, that's creepy. Either that, or you're in a bad relationship, you need to get out of it. Dump their butt. Okay? It's the PG way of saying that. You're not in a reciprocating relationship. Reciprocate means to return. If they return that affection for you, it's not a healthy relationship. Get out of there, man. Okay? But multiplicative inverse says when two people, two numbers really love each other, and they're reciprocals of each other, right? Because that's what true love is reciprocation. They multiply together and make 1. Aww. Aww. So here's a number, and here's its reciprocal. They multiply, bow chicka wow wow, and make 1 because they're in true love, reciprocation. Okay. Now, what is a reciprocal? It's a number flipped upside down. So write a number as a fraction, like 7 would be 7 over 1. So the reciprocal of 7 is 1 over 7. Aww, they complete each other. They make 1. They become 1. I know, right? Here's an example. -9 minus -9 is 0.
Wow.
Whoa, that's crazy.
What?
I know, right? We're adding -9 together with -9. -9 plus its opposite. What's the opposite of -9? -9. Also known as? 9. 9! You add them together, you get 0. German no, right? Okay. This one down here is 3/4. Its reciprocal is 4/3. Aw, they're reciprocals. So they multiply to make 1. Bow, chicka, wow, wow. Questions on that? Wonderful. Number 6. I will not be answering any questions about the birds and the bees. All right. Number 6. Properties of real numbers continues. The commutative property. All right. So the other ones are kind of weird, right? We had additive properties, multiplicative properties. We had the identity and the annihilation one, right? The one with the reciprocal and the one with the inverse. Here's where things get a little weird and people get confused. So commutative. It says adding or multiplying real numbers in any order. Order doesn't matter, right? Doesn't change the result. So a plus b is the same thing as b plus a. Always true for any set of real numbers. Doesn't mean it's irrational, whatever. They're always going to be in order backwards. This is true for addition and multiplication. It shouldn't be blowing anybody's mind, okay? That's commutative. In our community, you can do a plus b or b plus a. Just say what's up. Doesn't matter, okay? We're accepting here. That's commutative. The associative. The associative. When I hear associative, I think people at Walmart. When I think Walmart, I think me going in and messing with people. That's what I used to do as a kid. Now I don't go into Walmart because they're not unionized, and I don't want to spend money there that oppresses other people. Did you know that a lot of our tax money goes to paying people at Walmart because their wages they get for working, and they work really hard, aren't enough to keep them alive, so they have to get food stamps and other stuff, right? So because Walmart doesn't want to pay their employees a living wage, we end up paying them the difference.
So you're telling me not to look at Walmart?
That's not fair. I'm saying we need to stop buying stuff at Walmart if you can. Some people can't. I understand that. But if you can, you need to stop and help these people unionize. Whenever I do go to Walmart, because it's a necessary evil occasionally, right? I'm driving somewhere and I realize I need something and I'm in the nowhere. And of course, there's a Walmart, there's a monopoly in America, right? I have to go in and buy something. I always make sure I donate like double that to the local union. Seriously, these people deserve living wages. And Walmart's making millions of dollars off of them by paying them very little and having taxpayers like us subsidize the difference. All right, associative. So when I think associative, I think an associate at Walmart, right? The sum or product, sum meaning adding, product meaning multiplying, of real numbers is the same regardless of grouping. So grouping, A plus B plus C is the same as A plus B plus C. It's all about emphasis on the certain syllable. You picking up what I'm putting down, right? If you go to Walmart and be like, "Excuse me, sir, right, how may I help you?" Right? I'm looking for the DVDs. What? I need the DVDs. This messes people all the time, right? What am I saying? I need the DVDs. I changed the emphasis on the different syllable. So the wrong emphasis and the wrong syllable, right? So emphasis, A plus B plus equals A plus B plus C. It's all about emphasis, okay? That's what those parentheses are. They're emphasis. So that's Walmart. Associative. The distributive property. Distribution, okay? We're talking about redistributing wealth here. Socialism, let's do it. Okay, so distributive property. It says multiplying a sum by a number. Okay, so multiplying, we're doing some multiplication. We're going to multiply a sum. So here's a sum, two numbers being added together. We're going to multiply that idea, okay? We're going to multiply that sum. It gives the same result whether you add and then multiply, or multiply then add, okay? So you know this, you've seen it, okay? Let me draw it up, well, for the people at home, we'll do it on here, okay? You've seen this. So if I've got a sum, give me two numbers I'm going to sum together. Go, give me one. 5, everybody loves 5. Give me another number. 9, very good. So 5 plus 9. Now it says I'm going to multiply that sum by a number. What am I going to multiply it by?
4.
4, all right. So I can either do 5 plus 9 first, and that's going to be 4 times 14, and then I do 4 times 14. Pause, you can do this in your head. What's 4 times 10?
44.
What's 4 times 4?
16.
Add them together. 56. Nice job, kid. All right, or we can do this same problem, which really isn't a problem, it's a calculation. There's no problem here. This is boring. We can, instead of adding first, we can multiply. So we distribute. Remember this? Yeah, it goes to both terms. We'll talk about what terms are in a little bit. 4 times 5 is 20. 4 times 9 is 36. Checks out. So you can distribute, right? Distribute means to send out. So we take that 4 and we distribute it to the 5, we distribute it to 9, we distribute it to everybody, because that's what distribution is. It's fair and it's equal. Everybody gets the same. Okay? So you get a 4, and you get a 4, and you get a 4. That's distribution. I know, right? I know. Okay, so that was the joke. That's distribution. So if we have two numbers being added together, B and C, and A is multiplying them, we can write it like this, or we can write it like this, where A goes to both. Are you stepping what I'm smelling in?
What?
Are you smelling what I'm stepping in?
Yeah.
Okay, good. That was page 6, and I believe that was all of it, right? We have a page 7? Where's my page 7? There's a page 7? Oh, there's a page 7. Good. Okay. So we have examples. Everybody loves examples. Everybody loves examples. Here's the commutative property. 2 plus 3 is the same thing as 3 plus 2. Checks out, right? I did both. They both end up being 6, so they must be the same. If something is equal, it means it is.
Isn't 2 plus 3 5?
Okay?
Isn't 2 plus 3 5?
I know. That's the joke. Thank you for catching on. So, ruining my joke. That's fair. I understand you're smart. All right. No, it's fine. He's right. So, what I was going to say, before getting to the joke, which I'm not going to get to anymore. If something is equal, it means it's the same dumb thing. Okay? It's substitutable. These pens and pencils are the same. They're substitutable. You can use either on your exam, right? So if I tell you that x is 7, 7 can be switched for x and x can be switched for 7, right? So if I tell you that 2 plus 3 equals 3 plus 2, they should be interchangeable. Are they? Is 6 interchangeable with 6? Oh, yeah. The problem is that 2 plus 3 is 5. That's what you're saying. All right. If we add them like this, commutative property, associative, what is this? This one right here. Read the notes. It's associative. Remember, dividi is all about the emphasis. Parentheses are emphasis. Okay? We can check this as well. So here's going to be your homework. I'm going to go grab it from the other room. You're only going to do a little bit of it.
Power rings, we don't care. If you hear it, right?
Just about 3 halves.
Let's go.
Here's what I want you to do. You're only going to do the top half of this. This is an old assignment. I don't want you to do the bottom half.
So just the graph on the thing?
Yep. Just the chart, yes. So what you're going to do is you're going to put a check in each box that applies to the number.
Okay. What?
Okay? So let me put it up on the screen so you can see it. So check it out. You're going to do the chart. Okay? It gives you a number, and you're going to put a check in all the boxes that number exists in. What sets it exists in? Spoilers. What does every number exist in? What set does every number exist in? Real number. So all those numbers should have a check in the real. An X, a check, whatever you want to do. Just don't be the kid that puts an X for it not being in there. That's like kid. Get out now. Right?
Zero count as a number.
Oh, great question. Zero count as a real number.
That is a great question.
If you're not sure, look it up. Or look at the notes.
Yeah.
I'm not sure. Yeah, you can cross out the other. Remember, this is just a rough draft, so if you make mistakes, remember, we're going to go over tomorrow. Right? If you think that you did poorly, don't turn it in yet. Fix it, okay?
Just cross out the line.
Yeah, you can cross out the box.
Oh, I'm confused.
Uh-oh.
Wonderful. I think it means room for growth. You are?
Do we have to do that?
No. I think I screwed up. Well, I printed off all of this, but we aren't going to get to that stuff today. We aren't going to get to it later either, because I'm going to make a whole new worksheet. I don't like this much. Oh, yeah, you would. You would. You wouldn't.
Oh, you said this like you said,
Bro. All right, nerds. 8. Is 8 a real number?
yes.
Yes, it is. So we put a check right there. Everybody see that, or any change colors? Yeah, I would do the first one. Why not? All right, 8. Irrational. By the way, irrational is P. I'm not sure why. Okay. What I like to do is I like to start here. Is 8 a natural number? Oh, yeah, you count your sheep with that, right? Is it a whole number?
Yeah.
Whole number is all the naturals plus 0, so it still counts. What about integer?
Yeah.
Yep. What about rational?
Yeah.
Yep. So if it's natural, it goes all the way up.
Yep.
If it's whole, it goes all the way up from there. If it's integer, it goes all the way up from there, right? Can it be rational and irrational at the same time? No. They're opposites. See you later. Yeah, it is. I hope you feel like that every day. Because I don't assign a lot. How
Leave a comment down below.
Like the video.
Yeah, like and subscribe. I'll upload this later. It'll be on Google Class.